In this session, we will design L-section, T-section, and double L-section matching networks for the load defined in the previous session and compare the fractional bandwidths obtained to the Bode-Fano limit. Consider the equivalent circuit model for a certain load as shown, and we saw this load in the previous session. Design an L-section matching network for this load and compute the bandwidth for which the reflection coefficient is less than 1/3, compared to the Bode-Fano limit. Design a T-section matching network for this load, assuming Q equal 10, and compute the bandwidth for which the reflection coefficient is less than 1/3, compared to the Bode-Fano limit. Design a double L-section matching network for this load, assuming R sub D equals 25 ohms, and compute the bandwidth for which the reflection coefficient is less than 1/3, compared to the Bode-Fano limit. Okay, once again, here is the impedance of the load as a function of frequency. We have 14 minus J 91.7 ohms. Basically, we can model this as a series RC load. The Bode-Fano limit that we obtained in the previous session is 43.7%, and as we'll see, our actual matching networks in this session are not going to get anywhere close to that. Let's begin with the L-section matching network. We have a routine in MATLAB that we could use to make the calculations, and we see that we actually get all four possibilities here, two type A and two type B solutions. I'll just pick one. I picked the type B solution, the first one of those, so we have B sub B value and X sub B value here. And this gives us a series inductor and a shunt capacitor. And here I've implemented that in the ADS schematic. We have our load and we have our matching network. And simulating, we obtain the results shown all the way on the right, and we could use the markers to find the points where the reflection coefficient is equal to 0.3, and we can obtain the frequencies at which that occurs and calculate the fractional bandwidth, and we find that it's 4.2%, which is significantly less than the Bode-Fano limit. Now let's look at our T-section matching network and the design equations. Now, one thing I should note is that for the T-section, I can identify RL as 50 ohms and RS is equal to 14.0 ohms, but additionally, X1 prime is equal to 91.7 ohms. That is the, if we go here, X1, here's our load, consisting of a series RC. X1 is defined as a positive quantity, and therefore minus X1 is capacitive. So we find that X1 prime is equal to 91.7 ohms. Q is 10. So X1 is 140 ohms. X2 is minus 92.9 ohms. And X3 is equal to 261.2 ohms. So C1 then is the capacitance that we have to use in order to bring X1 prime up to X1, and that gives us a value of 3.60 picofarads. Since X2 is negative, minus X2 is positive, so that gives us an inductance of 16.2 nanohenries. And X3 then gives us a capacitance of 0.666 picofarads. So mapping from the previous figure, which gave us the recipe for the matching network, to the matching network itself, we obtain the following T matching network, and we're ready to simulate in ADS. And doing so, we obtain a fractional bandwidth of 2.9%. This is less than it is for the L section, as expected from a T section. And we see that we are, again, way below the Bode-Fano limit. Next, we'll consider double L section matching network. Notice that what I have here are two type A matching networks in cascade. The purpose of the first one is to match the impedance RL to the intermediate impedance, which we called R sub D. And then the second one matches R sub D to R sub S, the source impedance. So the first L section matches ZL to the assumed value of R sub D being 25 ohms. Again, we can run our MATLAB routine. We get all four possibilities. We're going to use a B possibility, and we'll take the one that produces a series inductance and a shunt capacitance, and we get a value of 18.1 nanohenries and 6.17 picofarads. The next L section matching network is the one that's going to match the 25 ohms to the 50 ohms. Again, we have a B-type matching networks. We don't have any A-type matching networks. The routine returns a NaN when we don't have that type of matching network. And then we can calculate a series inductance and a shunt capacitance. We find 4.35 nanohenries and 3.48 picofarads respectively for those components. And now we can implement our double L section matching network and simulate it in ADS. And when we do so, we can find the frequency range over which we achieve a reflection coefficient of less than 0.3, and we find that delta F over F0 is 4.3%, and this is more than it was for the single L section, which was 4.2%, but again, far less than that predicted by the Bode-Fano criterion. One thing I would like to point out is that when you have a double L section matching network, one of the advantages is you can actually use optimization to broaden the frequency range by not forcing a perfect match at the center frequency. That's and in fact, if you did that for both the L section and the double L section, you would likely find that the double L has significantly greater fractional bandwidth than the single L section. And that concludes this session.